Hey, it's me, Kylio, here to teach you Chemistry of Life from Chapter 2 in your textbook. So here's just an excerpt from the study guide pertaining to all things Chapter 2. And so let's start with atoms. So atoms are composed of protons, neutrons, and electrons. Your protons and your neutrons compose your nucleus. And we know that atoms are kind of the base component for all material that we experience. And then we also have, these are the subatomic particles, subatomic particles. We also have subatomic particles, but that's for another class. So protons and neutrons make up the nucleus. So your nucleus is going to sit at the center of your atom, and then electrons kind of orbit. Actually, they don't orbit, they blink around the nucleus. Protons have a positive charge, so P for positive. Your neutrons are neutrally charged, so they have no charge. And then your electrons, well, they have a negative charge. Okay, so as you may have learned in chemistry already, the electrons within your atom are actually what cause it to be reactive. And so what makes an atom reactive is, how an atom reacts to other things is it donates electrons, so it'll share electrons with other atoms, or it will completely donate, so relieve itself of its electron, or it will take or steal electrons from other elements. So electrons are what make an atom reactive. And so as you may have learned also in your chemistry class, is that you have these orbital shells that have certain amounts of electrons that stay within that shell. So we know that the first shell has 2 electrons, and then the second one has 8, 1, 2, 3, 4, 5, 6, 7, 8. And then your shell just outside of that should have 8 as well. Now, so the shells fill from the inside out. What I was trying to say earlier, I'm not sure if I have a slide dedicated to this, but when a shell is fully filled, the atom is considered to be stable. And so atoms have this natural tendency to either relieve themselves of their atom to make their outermost shell stable. So in that case, if this sodium were to relieve itself of this electron, then its outermost shell is now this shell, or its second shell, which would then contain eight electrons. Now, if you're talking about chloride, you actually have 7 electrons in its outer shell, and so since it's closer to filling up its outermost shell than to relieving itself of its outermost shell, it will actually have a tendency to steal electrons from other atoms. Okay, so elements. An element is just a substance that's made entirely from one type of atom. And the most common elements that we're going to find in living things are going to be carbon, hydrogen, oxygen, and nitrogen, or CHON. So CHON. And then we also have trace elements that make up a small percentage. And then here's your second most common elements that make up living stuff. But for the most part, just remember carbon, hydrogen, oxygen, and nitrogen. Okay, what was I trying to say here? This is the periodic table. I guess I could just talk about this. So hydrogen. Okay, so the way they're numbered. So hydrogen is our first element. It's going to have 1 proton. So the way we distinguish between the different elements or atoms is we number them by the amount of protons they contain. So hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, and so on. And as soon as you change the amount of protons, you're pretty much turning it into another, or not turning it into another, but now you're talking about another element. One thing that can vary between your elements is the amount of electrons and also the amount of neutrons. So hydrogen has one proton. It also, in its basal state, has 1 electron in its outer shell. Helium, we know that all of our noble gases are non-reactive because their outer shells or their outer electron shells are all filled. So they have no reason to interact or react with any other elements in the periodic table. Okay, so each element has a specific number of protons, giving it unique properties, and they're arranged on the periodic table by their number of protons. So we just mentioned that. Hydrogen, listed as number 1, has 1 proton. And so the other number that's listed is the atomic mass, and the atomic mass is going to be the combined mass of your protons and your neutrons. And the number of neutrons, like I said earlier, may vary between the different atoms. So a different form of an element, we call that an isotope. So sometimes isotopes can be radioactive. Okay, so here's a question. The 4 most common elements in living organisms, remember we mentioned carbon, hydrogen, oxygen, and nitrogen. So carbon, hydrogen, oxygen, nitrogen. This is sodium, and this is iron. So C would be the correct answer. All right. So atoms whose shells are not full tend to interact with other atoms and gain, lose, or share electrons. So your outermost shell, so this is labeling the outermost shell can hold up to 8 electrons, and the first electron shell can hold 2. So if we're talking about hydrogen, remember, we've got 1 proton, and then they also have 1 or, they'll in their basal state or in their neutral state, they will contain 1 electron. And so this hydrogen can relieve itself of its electron, or it could gain an electron, or it could share its electron. And we'll talk about that when we get to covalent bonds. So carbon, and so also looking at the valence shells and seeing how many open spaces there are kind of help you determine how many bonds they can make when they are making covalent bonds. So here, hydrogen, if it were to make a covalent bond with something, it can only make 1 bond because it's got 1 open space. But if you're looking at this carbon here, you got 1, 2, 3, 4. So it can make bonds with 4 other elements. Nitrogen can make 3 bonds with other elements, and then oxygen can make 2. So which of the following particles is found in the nucleus of an atom? Remember, we've got protons and neutrons, so that's C. Okay, so sodium and chlorine. All right, so we'll probably be talking about ionic bonds here. So, or actually, we're just talking about the way we interpret their mass number and atomic number. So if we're looking at sodium, which is denoted with an N and an A, and we look at their sodium's atomic number, it says 11. So its atomic number means, or the atomic number is the amount of protons it has. So its atomic number is 11, therefore it has 11 protons. Now its mass number is 23. So remember, if the mass number is the combination of protons and neutrons, then all we have to do to determine the amount of neutrons in the nucleus of this sodium atom is we subtract 11 from 23. So 11, or 23 minus 11 would be 12, right? So 12 neutrons in this sodium atom. And then with chlorine, same thing, atomic number 17, it's got 17 protons. Its mass number is 35, so 35 minus 17 is 18 neutrons. Okay, so sodium atom that contains 11 electrons, 11 protons, and 12 neutrons. What is the mass number of sodium? Mass number is the protons plus the neutrons. So you've got 11 plus 12. What do you get? 23. A is 23. All right, now we'll talk about ionic bonds. So when atoms gain or lose electrons, charged atoms called ions are created. So remember, your atoms have the tendency to neutralize or to fill up, I guess you should say fill up or remove its outer shell. So sodium is very close to having no outer shell and just having this outer shell pick it up after you relieve yourself of this electron. Chloride is much closer to filling up its entire outer shell. And so these two elements work together to kind of generate homeostasis, or not necessarily homeostasis, to generate stability. So what happens is your sodium will give up its electron in its valence shell, and chlorine will steal that electron. So now chlorine's outer shell is satisfied, it has 8, and now sodium's outer shell, which is this new outer shell, the shell below this outer shell, picks up, and it has 8 electrons, so it's now neutral, or not neutral, I shouldn't say neutral, but stable, more stable. And so as a result, we get sodium ion, a sodium ion, and a chloride ion. So this, when you start working with ions, it'll make more intuitive sense to be able to denote what charge they have. So what happens is sodium loses an electron. Electrons are negatively charged. If you're losing a negatively charged thing, so you're becoming less negative, you are therefore becoming more positive. Chloride, on the other hand, it has received a negative thing, so it's becoming more negative, and so as a result, it has a negative charge. And so we call these differently charged ions different things. So if you've got a positive charge, so sodium has a positive charge, we call it a cation. The way I like to remember this is because cats are positive, more chaotic neutral in reality, but they're positive, cats are positive, and then anions, those are negative. And I guess the way you can remember this is there's an N, anti-cat, anion, has a negative charge. Okay, so we talked about ionic bonds. Now we're going to move on to covalent bonds. So when you're not very close to one or the other end, oftentimes you'll have a tendency to share electrons rather than give them up or steal them entirely. So two atoms that share a pair of electrons form a molecule, and that molecule's bound together through a covalent bond. So this is a stronger bond than ionic bonds. Also, I need to mention, you've got a positive charge, you got a negative charge. These things will usually form an ionic bond with each other because of the disparity in their charge. You've got a positive charge, you got a negative charge, and those opposites attract. Here, you've got a stronger bond, because what you're doing is you're now, instead of just giving an electron from one atom to another, you are sharing electrons. So remember, hydrogen has 1 electron in its outer shell, but remember, its outer shell can contain up to 2. So to stabilize its outer shell, what happens is, well, you can bond, or you can form a bond with another hydrogen, which is looking for the same thing. And so what happens is you form dimolecular hydrogen, or H2, and they're sharing that electron with each other. So the electron from one hydrogen is plugged into that hole of the other hydrogen, and then the other hydrogen's outer electron is plugged into the hole of the other hydrogen. So they just form a bond with each other. Same with oxygen. Remember, oxygen can form 2 bonds. And so what happens is here they're sharing these 2 electrons, but they're also sharing these 2 electrons in addition. And so you form a double bond. A better representation, I should have jumped from H2 to water. So oxygen can form 2 bonds. So here's a bond with hydrogen, here's another bond with hydrogen. If you want to form dimolecular oxygen, you're just forming, remember they can have 2 bonds with another oxygen molecule, or another oxygen atom forming a molecule. And then carbon, what makes carbon so unique is that it can form 4 bonds, up to 4 bonds. And so it's a very, very versatile atom. And in this case, we show you methane, which is carbon bound to 4 other hydrogen atoms. Okay, so what is the fundamental difference between covalent and ionic bonding? All right, so let's just read this from A to D. In covalent bonding, both partners end up with filled outer electron shells. In ion bonding, one partner does and the other does not. That's false, because in ionic bonding, you now have 2 filled outermost shells. You have chloride, for example, which has gained an electron. You go from 7 to 8, and then you have sodium, which has yielded its outer electron. Now it resorts to the outer shell just below the original outer shell, which was at 1.1, and now you have a full outer shell, which is 8. Covalent bonds form between atoms of the same element. They can. Ionic bonds form between atoms of different elements. No, I would say this is incorrect, because covalent bonds can form between atoms of different elements, and ionic bonds form between atoms of different elements. That's not a requirement. So none of these are necessarily requirements. These are just things. Covalent bonding involves only the outer electron shell. Okay, fair. Ionic bonding also involves the next electron shell inside of the outermost shell. Let's come back to that one. In a covalent bond, the partners share a pair of electrons. In an ionic bond, one partner accepts electrons from another. That one's correct. Let's go back to C. Covalent bonding involves only the outermost electron shell. Okay. Ionic bonding also involves the next electron shell inside the outermost shell. I would say that's false, because there's special cases where that wouldn't happen. This is the simplest, and this is the most correct of the 4 potential answers. So in a covalent bond, partners share. In an ionic bond, something is stolen from another. Okay. Polar molecules. So we talked about ionic bonds, we talked about covalent bonds. Now we'll just talk about polar molecules in general. So water is the prime example of a polar molecule, because it's polar. If you think of anything that is polar, it is polar because one side is different from another. And so if we're looking at water, for example, you've got your oxygen and you have your 2 hydrogens. Now, if you were to draw a line anywhere separating one half of this molecule from the other, you're going to get 2 separate halves. So if you draw a line, actually, I should make the distinction for nonpolar. But I'll use the example for polar. So because you can draw a line that makes one half of the molecule distinct from another, it is therefore polar. So here you can draw a line right here, and you've got 2 hydrogens on one side, and you got no hydrogens on the other. Therefore, it's polar. So part of the molecule is more positive, called partial positive, and part of the molecule is more negative, called partial negative. And so here you have your hydrogens, and this might be a little bit more chemistry than you'd like to hear, but you are likely going to hear this if you haven't heard this already, you are going to hear this in your chemistry course. So there's this concept called electronegativity, and oxygen has more protons in it. if it has more protons, which are positive, the electrons, which are negative, are going to be drawn to those positive protons more intensely than the single protons found in the nucleus of your hydrogens. Therefore, if oxygen has a higher electronegativity, what's going to happen when you form these covalent bonds is that the electrons are going to spend more time closer to the center of the nucleus or closer to oxygen, which contains more positively charged particles. So you're sharing this bond between oxygen and hydrogen. The electrons are going to gravitate towards oxygen more often, or gravitate towards oxygen more so than hydrogen. And so what happens is these hydrogens form what we call a partial positive charge, whereas your oxygen forms a partial negative charge. So there's more electrons hanging out around this oxygen than there are around these hydrogen molecules or atoms. And so that's another thing that makes it polar. So you have the spatial distribution, right? You have the spatial thing, or I guess you could just say the visual way of determining if something's polar versus nonpolar. But you also have the concept of your electrons hanging out more towards one end of the molecule than the other. And so we know that opposites attract. These partial positives are drawn to partial negatives. And so oftentimes what happens when you have a lot of water together, these partial positives are going to hang out. They're going to form these what we call hydrogen bonds. So the attraction between this hydrogen with a partial positive charge to this oxygen with a partial negative charge. Okay, so we got a nonpolar molecule. So methane is a prime example. You cannot draw a line anywhere within this molecule that would yield a different distribution of electrons anywhere between one side or the other side of the molecule. So if you were to draw a line through the center anywhere, even using 3 dimensions, you would not be able to find a slicing point where one side would be different from another. So it makes it nonpolar. And as a general rule of thumb, nonpolar stuff will dissolve nonpolar stuff, and polar stuff will dissolve polar stuff. And so that's what makes water a really good solvent. What makes water a really good solvent for polar stuff is the fact that it is a small particle or a small molecule that has polarity in general. So most of your fats, they're going to be nonpolar. So methane and any kind of fat, they would dissolve and they would become kind of homogeneous in a solution. Whereas water and like salt, for example, and we'll talk about that, they become kind of homogeneous. You can't really just you can't distinguish between the water and the salt if everything is dissolved. Okay. So in a water molecule, oxygen exerts a stronger pull on the shared electrons than hydrogen. Partial negative charge on the oxygen. This makes the oxygen end of the molecule slightly negatively charged. The hydrogen end of the molecule is slightly positively charged. Water is therefore a polar molecule. So the attractive force between the partial positive of the hydrogen of one water molecule and the partial negative area of another molecule. So here's your hydrogens, partial positive attracted to that partial negative of that oxygen. And here you've got the partial negative of this oxygen, which attracts the partial positive of this hydrogen, the partial positive of that hydrogen. So water tends to stick to itself. We call that cohesion. So a solvent is something that dissolves other things. Water is a good solvent because, like I said earlier, it is a small molecule that is polar, and so it's really good at dissolving polar things. Your solutes, those are the things that are becoming dissolved. So let's take table salt, for example, sodium chloride. They're usually contained within, or they're usually, they adopt the formation of a crystal where you have that positively charged sodium attracted to that negatively charged chloride ion, and they form this crystal. Now, when you drop salt into some water, what happens, because water is polar with a partial positive and partial negative on one side of the molecule, or with a partial positive on one side of the molecule and a partial negative on the other side of the molecule, what happens is you get those partial positives of those hydrogen atoms within the water molecule attracted to the negative charge of your chloride ion. And then you have that partial negative charge of the oxygen attracted to that positive charge of your sodium. And so essentially what happens, this is how things become dissolved, is water separates those two atoms from one another, and it forms this bubble, almost like a bubble around it. So it separates these ions from each other, and now they're just floating in solution. We call this an aqueous solution. So here's some unique properties of water. The reason it is not like any other substance. So it's like no other common substance, and it exists in nature in 3 physical states. So we've got liquid, we've got solid. So liquid would be water, solid would be ice, and gas. Where's this gas? Oh yeah, so it's vapor stage. That's just another stage. So the least, so liquid is actually your densest state, and solid is not as dense. So if you look here, we've got liquid, and the hydrogen bonds kind of keep each water molecule closely tied into each other. And it's fluid, so they can move around, it's jiggly. However, when you have ice that forms, what happens, and this is a little bit of a deeper chemistry topic, but it kind of stretches out those hydrogen bonds. It stretches out those bonds that hold the water to other water molecules, and therefore it's less dense. Things that are less dense will float on top of things that are more dense. So it takes a lot of energy to break apart hydrogen bonds. Now, when we're talking about a large body of water, you've got water molecules bound to other water molecules, bound to other water molecules in a high density with a high population of water molecules. And so because it takes a lot of energy to break a single one of these hydrogen bonds, the sheer amount of hydrogen bonds that you would have to break to cause water to evaporate is actually very high, or to even change the temperature of water. So in order to change water temperature, these hydrogen bonds must be broken. So it takes a lot of energy to actually cause temperature change in water. That's why it's a great temperature buffer for the body, for example. So water is able to absorb a great deal of heat, energy without a large increase in temperature. So here's some terminology. We have cohesion, so that's water molecules that stick to each other to form droplets, so cohesion. And then adhesion, that's where they stick to other surfaces. So adhesion, you're adding something new to the water. So you'll probably see this when you take OChem, or you'll probably talk about this in your Gen Chem, but there's a process called capillary action. This is where water or fluids will actually raise, for example, let's say this is a cup, and you have a straw dipped in the cup. Usually what you'll see when you have a straw submerged in a cup is you'll see that the meniscus, so where the water stops, it's a little bit higher than where the water stops in the cup. So where the water will stop within the straw will be a little bit higher than where it stops in the cup. And so what happens within that straw is water will actually cohere to itself, but then also adhere to the side of the straw, and then cohere to itself, and then adhere to the side of the straw, and then cohere to itself, and then adhere to the side of the straw. That was a weird stutter. And so it actually will rise. It'll rise on the sides of the straw. And then likewise, if you're looking at, let's say you spill you spill a bunch of water and you have like some porous surface, it'll just climb up the wall. Or for example, let's say you dip a piece of paper in some water, you'll notice that the water will actually climb up the paper. That's because of adhesion and cohesion. We call that capillary action. And so when water evaporates, it actually takes a lot of heat with it. And so that's what gives us evaporative cooling. It's not cooling us down, it is pulling away heat. So water molecule takes a large amount of energy with it when it evaporates. Okay, so hydrogen atoms within a water molecule are bonded to the oxygen atom by what bonds? Whereas neighboring water molecules are held to each other by what bonds? So hydrogen atoms within a water molecule are bonded to oxygen by, so we're talking about a single molecule of water, H2O. How is the oxygen bound to the hydrogen in H2O? Those are covalent bonds. So we look here, polar covalent, polar covalent. Okay. The reason why we add that polar to it is because there's an unequal electron distribution within that covalent bond. So we've cut out A, we've cut out D, we've got B and C. Now, the neighboring water molecules, they're held together by what kind of bonds? Hydrogen bonds. It involves hydrogen, and it's a bond between hydrogen and some partially negative molecule. So we've got polar covalent, that's within the water molecule, and then hydrogen bonds between water molecule and water molecule. Okay, so acid-base reactions. We're not going to get too deep into acid-base reactions in this class, but we do need to know the difference between a base and an acid and how they fit on the pH scale. But we'll generally go over what an acid is. So an acid is something that yields hydrogen, and a base is something that will remove or pull in hydrogen, or something that will yield hydroxide. So hydroxide has a negative charge, hydrogen has a positive charge. When you combine those things together, you actually get water. So hydrochloric acid is an acid. Potassium hydroxide is a base. You add those things together, what you're going to get is potassium chloride plus water, because this hydrogen binds to that hydroxide ion. And then I guess here we use a completely different formula. So you've got hydrochloric acid, and then you have sodium hydroxide. You make table salt and water if you add them together. So the most important part here, the most important takeaway about acids and bases is the pH scale. So if your pH is below 7, you're acidic. So urine, saliva, tomatoes, vinegar, cola, so Coke is at a 3 in pH. And then if you're neutral, then your pH is at 7. So just pure water, no hydrogen ions, no hydroxide ions, or an even distribution of hydrogen ions and hydroxide ions. Now, if your pH is above 7, that's when we consider it to be basic. So things like oven cleaner, sodium hydroxide, or household ammonia. So the higher you go in the pH scale, the more basic you are, and the lower you go, the more acidic you are. And then buffers, those are just chemicals that minimize the change in pH. So something like a salt in a solution, let's say you have some water with a buffer in it. Oh no, let's say you just have water, okay? And then you add a bunch of stomach acid to that water. So that water, which was originally 7, might move closer to like 3 or 4, depending on how much stomach acid you put into it, right? So it'll drop drastically. However, if you have a buffer in that water, so let's say you have that same jar and you have a buffer in it, and then you pour stomach acid into it, instead of moving to a 3 or 4, it might move to like a 5 or 6. So it prevents the drastic change in pH due to the addition of a base or an acid. So it can go the other way as well. Oh, that's it. All right. Well, I won't see you. Goodbye.